Okay, from the last video, I was just talking about waves passing through a narrow opening and actually bending around around a corner, and that's called diffraction. All right, so only waves can do this. For example, if you had a narrow opening and you were shooting bullets, which would represent particles, bullets never go around the corner. That never happens. So only a wave can do that. In fact, that's why if you pick up a you go around the corner of a building, you can still hear a radio station if you happen to be listening to a radio station. All right, so that's what's called diffraction. There's another phenomena. I guess it's not really showing it here. It's also called interference, when the two waves interfere with each other. So basically, what happens is the waves can either add together, or here let's take a quick look at a wave. If you have a wave that's going up and down, and then what happens is you can have you can basically split the wave off, and you can either two crests could meet, or two troughs could meet, and so you get more of the wave. That's called constructive interference. And then when a crest and then for the second wave, a trough meet at the same time, that's called destructive interference. All right, so that's actually used a lot in astronomy, as well as this diffraction phenomena. So both of those are wave type things. All right, so here's another thing. Let's talk very briefly about the what's called the Kelvin scale. Of course, you know about the Fahrenheit scale. Water freezes at 32 degrees Fahrenheit. The human body is at about 98 point something. Water boils at 212 degrees Fahrenheit. And then there was another scale called the Celsius scale. Sometimes it's called the centigrade scale, where water freezes at zero, and it's actually the Celsius scale is based on the freezing point and the boiling points of water, of liquid water. Anyhow. Or when liquid water turns into a solid, or when liquid water turns into a gas. Anyhow, that's the Celsius scale. Notice both of these scales, the Fahrenheit and the Celsius, have a lowest temperature. There is so the lowest value is in there. Temperature has to do with movement, the movement of molecules, the movement of atoms, and so when all movement stops, you have a lowest temperature, an absolute zero, and so this absolute zero, which is negative 273 on the Celsius scale, negative 459 on the Fahrenheit scale. There's a whole other scale that pretty much only people in science use, called the Kelvin scale. And so the Kelvin scale starts at zero, of course, but where there is no negatives, right? So that is the lowest possible temperature. All motion would completely stop at zero. And we can, like in our laboratories, for example, just to let you know, we can never actually get to zero, all the way to zero, but we can get within a small fraction of zero. So we can almost completely stop the motions of atoms, but you can't completely stop stuff. Like electrons are still moving around, and that causes a little bit of thermal energy, and so there's a little temperature. But we can, like I said, in our laboratories, we can get with really, really good vacuums, we can get down to just a fraction of zero. All right. And then, so the freezing point of water is 273. Roughly room temperature, or an average 70-degree day, let's say, is about 300 Kelvin. So that's actually a good temperature for humans and most life to exist at. Water boils at 373 Kelvin, and just to let you know, we've actually measured the temperature of space, the average temperature, like out there between the galaxies, and the average temperature of space is about 2.7 Kelvin. Now, if you aim your telescopes at a star, it's much hotter, and we can actually, that's actually the point of this part, is we can actually tell from the light what the temperature of a star is. Because starlight is in the form of what's called black body radiation. Not any light is, not all light is black body radiation, but when something is emitting light because it's hot, that's what's called black body radiation. All right. Anyhow, the temperature of the sun, the surface temperature of the sun is at about 6,000 Kelvin. So it's not the center of the sun is at about 10,000. I'm sorry, about 10 million Kelvin, and that's actually where hydrogen, the hydrogen atoms, the protons, fuse into what's called helium, and that's actually what causes the stars to emit energy. Hydrogen is turned into helium for most of their lives. All right, so anyhow, the surface temperature of the sun is at about 6,000 Kelvin, and that's an important number. All right, so this is the traditional or the classic, what's called the black body curve. Okay, so the black body spectrum, and all things that are emitting light because they're hot have this characteristic curve. And so you look at the light, you break it into its spectra, and you can tell what the highest wavelength is, or the highest frequency. So whatever the highest wavelength is, the peak wavelength or the peak frequency, you use that to determine what the temperature is. Excuse me. So there's actually a formula. Let's see. I don't know that you guys have that formula here. Let's see. It's called Wien's law. I don't know. We don't have to actually have the actual equation, but if something, for example, has a peak in the ultraviolet, it's much hotter than something that it has a peak in the red part of the spectrum. So our sun is, of course, a yellow star, so it peaks right around the yellow, which makes it at 7,000, at roughly 6,000 Kelvin. So there are stars that are much cooler than the sun, reddish stars. They're generally called red dwarfs, and so they can peak in the actually in the infrared, but that we see them as red stars, or very dim red stars, and so they are much cooler, and actually they turn out, our star, which is a yellow star, is kind of a medium star. There's stars that are much hotter than the sun. There's stars, in fact, that's what I was trying to say. Most of the stars in our galaxy and galaxies around the universe are actually these relatively low mass, low temperature stars that are actually peaking in the infrared. So our star is kind of a middle of the road star. It's a yellow star, and again, there's stars that are much higher temperature. All right, so that's called the relationship between the peak wavelength and the temperature of the object is called Wien's law. All right, and Let's see, are they showing you? All right, so I guess they're not showing you the equation. That doesn't. Oh no, there it is. Here it is. Here it is. I knew it was in here. All right, so yeah. So this is how to tell the if you measure the peak wavelength, then you could actually calculate the temperature. So this is just the equation that you would use, and then, so it's called Wien's law. All right, very nice. So, oh, this is the Stefan Boltzmann constant. Yeah. So, the energy that a hot object is emitting is proportional to the fourth power of the temperature, and it's related through a constant called the Stefan Boltzmann constant. That we're not going to do any actual calculations with this, but you're just yeah. And not a lot of books use. I don't know why these PowerPoints are using F here. F is usually reserved for force, but it's certainly not a force. It's an energy per unit area, as it says here. All right. Anyhow, that's beside the point. There's the value for the Stefan Boltzmann constant. It's in watts per square meter per watts per square meter times Kelvin to the fourth power. Not like I said, we're not actually going to use this. You're just looking at it here. All right. So what about the Doppler effect? So it's also known as the Doppler shift. Sometimes you hear people talking about it. So what happens is you talk about a source of radiation. So it could be somebody on a bicycle turning on their light, turning on a flashlight or something like that. But also the Doppler effect is true for all waves, whether it's water waves or sound waves. And so it works, like, for example, if you hear a siren, like a fire engine or something like that has its siren going off, you can actually tell whether it's moving towards you or away from you because of what happens with the wave, right? Actually, there's a nice video, or there's a nice. This is just the equation right here. This is the relationship, but there's you can kind of see it right here. So when something is moving away, what happens is the waves get stretched out. If something is moving towards, the waves get scrunched together, and so in terms of light, so this happens with sound. It also happens with light waves. But generally we talk about either something is blue shifted, so that means it's moving towards us, or if something is red shifted, the light is more towards the red end of the spectrum, and so we can actually measure that quite well. And in fact, when a cop, if unfortunately this ever happens to you, if a cop pulls you over and they've got their radar gun out, that's exactly what they're doing. Is they bounce the radar off the car. Usually they use the license plate of the car because it's a nice flat region, and so there's electronics that will tell the cop exactly how fast you were going. That's how the Doppler shift works. All right, and the other thing is, you really can't get yourself out of a ticket by explaining to the fine officer how the Doppler shift works. They don't really care. All right, so anyhow, I'm speaking about through experience on this. All right, so we you can measure velocity. This is the equation that's used. I don't know that we'll actually use. I don't think we'll actually do any calculations with this, but this is the relationship that is used. All right, is basically you observe how the wavelengths changed, then you compare that to a wavelength